out and I make this be x, you solve it the same exact way. It's an equation. It has an equal sign. So how would you solve? You'd add 1. So we're going to do the same thing over here. We're going to add 1 to our trig equation. They keep your variable. Now, how would you do this one on the right? What's the next step? Divide by 2. You need to solve for x. So you solve. Now, divide by 2. We need to solve for the variable, which is the sign of x. Okay, now, we're done with the algebra part. The reason why this is called the trig equation, because now once we finish the algebra part, we have the trig part to do. We are no longer on restricted domains. We are back to your regular full sine curve. And your sine curve is endless. So there are many angles that have a sine of 1/2. See them? A lot of angles have a sine of 1/2, and they keep on going. So if we want to find all the solutions, we have to keep our circle going too. And the way we do that is we start a circle and we keep on going and going and going, and we keep adding 2n and 2n and 2n and 2n until we find all our angles. We kind of use the concept of a terminal sign, the coterminals. So we think back to our 4 quadrants, no longer restricted, and we say, okay, where is sine, the y value, positive? What quadrants? First and second. So we drop a triangle here, y over r, and we look for our reference angle. So what's our reference angle? This guy right here, 30. Okay, so now, let's work this in degrees for a second, so we get the concept. So if my angle is 30 degrees here, and my angle is what over here? 150. Now, think back to the concept of terminal angles, coterminals. It's going to terminate at the same point. So if I came up here already, if I go all the way around again and add 360, won't I come back to that point again? So if I keep adding 360, then I get 390. Then I add 360 again, right? Won't I keep finding all my angles? So I have the concept of adding, keep adding 360, keep adding 360. Now, we're going to flip this into radians because the radians make a little bit more sense. How do I say, how many times does 30 go into 180? So this is 6 pi over 6, and this is 12 pi over 6. So let's go with your angles. So this is your 1 pi over 6, and this guy is what? 5 pi over 6. Now, remember, we added 360. We could add 2 pi. 2 pi. Get another 2 pi. Add another 2 pi. Add another 2 pi. If we keep adding 2 pi, we'll find all the possible solutions that we can. But this would take us a really long time if we had to do this, if we had to find all solutions. So think back to where we did the restricted domains on the domains for your tangent and stuff when we kept doing the tangents. We put a little n in here. It's harder to do with the 360, but you can do it easier with this guy. If we say 2n pi, where n is any integer. And let me explain this. It's the same as you just told me. Add 360, add 360, add 2 pi, add 2 pi. So I'm at the 0, so I get this angle. N is 1, I add 2 pi. N is 2, I added another 2 pi. N is 3, I added another 2 pi. So all my possible solutions, endless, because I can't certainly do this forever and ever, right? I have to find a way to qualify this, is between pi over 6 and every 2 pi after that, so 2n pi. That's all solutions. These are endless curves, aren't they? I have endless angles. Infinite amount of angles that have a sine of 1/2. They keep on going forever and ever. So how will I say that? I will just keep adding 2 pi to those two angles. So then I have to come back to the same terminal side. Add 2 pi, add 2 pi, add 2 pi. So the first time through, guys, I add 2 pi. The second time through, I would have added 4 pi. Then I would have added 6 pi. Then I would have added 8 pi. So it's the same as 2n. These are all the times I would add pi. It's the same as this. 2 times 1, 2. 2 times 2, 4. 2 times 3, 6. 2 times 4, 8. See it? 2n pi. These are all solutions. This is totally the opposite of what we did last week. Last week we did inverses, restricted domains. You were just limited to 1 quadrant or 2 quadrants, whatever, 2 quadrants, whatever 2 quadrants we looked at. This is the complete opposite. Make sense? It'll start making a little bit more sense as we do a couple more. Okay. Let's go to this guy. Okay? So this looks a little bit weird. So let me replace the sign of x and make it look like this. Whoops. Let me replace this like this. How would you solve the equation on the right? Got to get x by itself. Subtract. Subtract what? Subtract x. You can deal with negative numbers. You're good. You got to solve for x. Divide by negative 2. Okay? Now, do the same thing here. Here's our variable. You have to get the variable to one side. So the same thing you did here. Just subtract sine x. Same process. Divide by negative 2. When you can't see that with sines and cosines, take them out and look at them first. Radical 2 over 2. Sound familiar, radical 2 over 2? It's something rationalized, right? It was your negative 1 over radical 2. Anybody remember what angle that was? 45. So where is sign negative this time? 3 and 4. Good. So it's 1 over radical 2. This was your 45-degree angle. In radians, how many times does 45 go into 180? 4. 4 pi over 4, 8 pi over 4. So this guy down here is what? 1 more than 4. 5 pi over 4. And this guy over here is 1 less than 8. 7 pi over 4. Now, if we wanted to stay just in your unit circle, just in 2 pi, or just in your one trip around, that would be our answers. But we wanted all solutions. So, think of your coterminal side. I take this guy, and I have to add another 2 pi. Add another 2 pi. Keep going and adding 2 pi to that. So, if we add 2n pi to both of these, where n is any integer, we found all possible solutions forever and ever and ever along that curve. Forever and ever. 2n pi. Right? We're adding 2 pi, then 4 pi, then 6 pi, then 8 pi. Okay? Now, the second part of this says, what if I want only my solutions from 0 to 4 pi? Which means I already did 2 pi, right? I found this solution already. All I have to do is come one more step around. Maybe this will make you kind of see it a little bit better. So if I add 2 pi, doesn't that bring me to 4 pi? So let's see what happens. I'm going to take this guy and add 2 pi. And add 2 pi. Now, the nice part about if you lay this out in radians, and you look at the way this goes, isn't 8 pi pi over 4 the same as 2 pi? So when I add a fraction and a whole number, don't I have to convert the denominator to the same denominator? If I add 1/2 plus 2, how do you add that? Don't say 2 1/2. Put 2 over 1. We've got to find the same denominator. So we multiply, and now we could add 4 over 2. Right? So, same concept. 2 pi is equal to what? 8 pi over 4. I want this denominator. So I got to set this equal to 4. 8 pi over 4, which is what you found already over here. So if I add 8 pi over 4 to 5 pi over 4, my denominators are the same. I get 13 pi over 4. If I do the same here, make it be 8 pi over 4. I get 15 pi over 4. So I have 4 solutions. 5 pi over 4, 7 pi over 4, 13 pi over 4, and 15 pi over 4. Those are my 4 solutions to go 2 pi, then another 2 pi, or 4 pi. Every 2 pi has to give me 2 angles, doesn't it? So doesn't 4 pi have to give me 4 angles? Right? 2 pi, 1 is 2 pi, and again. I'm just adding 2 pi to it. We're using the concept of coterminal angles. It's going to terminate at the same place. So first we find all solutions, and this is key. This is endless. My curves are endless. And then we find it within a certain range, from 0 to 4 pi. Getting a little better? All right, let's try one more. Now, the reason we're adding 2 pi is because your cycle of sines is 2 pi. Doesn't it take 2 pi to complete one full cycle? Your period for sine is 2 pi. So the cosine, and I should have done one sine, one cosine. The cosine is going to work the same exact way, because isn't the period for cosine also 2 pi? It makes the complete revolution in the 2 pi. Okay, now we're going to see one that works a little bit different. Tangent. So let's pull this down here. Okay, so my first step. What should I do first? Minus 3. It's an equation. Then what? Divide by 3. This is sounding familiar. So the tangent is equal to -1. What angle has a tangent of -1? 45. Okay. Now, where is tangent negative? What quadrant? 2 and 4. Good. And we know that this is a 45-degree angle. Work radians, it's so much easier. Now, how many times does 4 go into 180? 4. So 4 pi over 4, 8 pi over 4. So what's this first angle? 3 pi over 4. And what's this second angle? 7 pi over 4. Now, I want to show you something different on the tangent. The period for the tangent is every 180 degrees. Every pi degrees. Guys, I really need your attention for this. When we did the sine, look, they were opposites each other, right? They were either in the same, the same type of quadrants. And the cosines, therefore, the cosines will look like this, positive and negatives. They're next to each other. The tangents are opposite each other. Negative, negative, positive, positive. So if I use my coterminal angles, and instead of going every 2 pi, if I go here, I'm only 180 degrees away from here. Right? So if I just take the first one, and I keep going every 180 degrees, will I hit an angle? 180 degrees, 180 degrees, 180 degrees. See it? So if I take my first one and I add n pi, that's a little bit of a shortcut. If I only use the one and I keep adding 180, 180, 180, won't keep bringing me back and forth, I could take the first one and add 2 pi. I could take the second one and add 2 pi. But because I'm completely opposite, I'm 180 opposite, I can add n pi, n pi, n pi, n pi, and get there. If I add n pi, and your n pi is 4 pi over 4, right? If I add 4 pi over 4 to 3 pi over 4, what do I get? 7 pi over 4, so 180. If I add 4 pi over 4, I get 11 pi over 4. There I would be, 11 pi over 4. Because otherwise this would be 12 pi over 4, okay? This would be 3 pi. So I just have to keep on the tangent and the cotangent. The cycle is the period is every pi. So I just keep having to do the 180 part. So I can get all solutions just off of one angle. Now stay with me. We're going to take this concept and we're going to bring it into here. From 0 to 4 pi. So we're going to convert this guy. Instead of adding pi this time, pi is the same as 4 pi over 4 with the same denominator, right? 4 pi over 4. So we're going to keep adding 4 pi over 4. So this is how we start. Now we want to stop when we hit 4 pi. Here's our stopping point. Convert this to over 4. So what would be my numerator? 16 pi over 4. So when I hit 16 pi over 4, I'm going to stop. Rather than keep adding and have to keep checking. This is where I stop. So I start with 3 pi over 4. This is nice. You just keep adding 4. What's my next angle? 7 pi over 4. What's my next angle? 11 pi over 4. Did I hit 16 yet? Nope. Add 4 more. 15 pi over 4. Up. If I add more, won't I be over 16? So, 4 angles. See if it makes sense. 2 angles in 2 pi. 2 more angles in 4 pi. Shouldn't I get 4 angles? Okay. Now I know this is a little bit of a different concept, but it makes sense. If you do it in radians, it's far easier because you'll be able to keep adding them. And if you do this, this is your n pi, and this is your 2n pi. So we're adding 2 pi, adding pi. Good? Tangent's a little bit different because it has its own cycle. Okay, let's see if we can squeeze this last one in. This one works a little bit different too. Alright, so how should I solve this? This is my variable. Add 1. Divide by 3. How do I undo a square? Square root. Remember, when you take the square root, you get a positive, negative. So, this takes me to all 4 quadrants, positive and negative. And my tangent is 1, y over x, radical 3. What's my reference angle? All I need is 1 reference angle. 30. How many times does 30 go into 180? 6. So this is 6 pi over 6. This is 12 pi over 6. Now, I need to find all, did I say find all solutions? Find all solutions. Oh yeah, there. Find all solutions. Now, this is endless. It keeps going and going and going. But now let's use your concept, guys. If I go here, if I add 180, won't I get to this guy? So this one, I'm going to start here. Pi over 6 plus n pi. And then which other angle should I do and do its opposite? I took care of this one and this one. 5 pi over 6 plus n pi, where n is any integer. See it? They're complete opposites. Complete opposite is 180 apart. So I don't really have to do all four and say 2n pi. I just have to pick the opposites. Okay, try these